first talk is just going to be a general one on radiogenic isotopes, but not from the perspective of dating, more from using them as isotope tracers and sort of fingerprinting different chemical reservoirs we have in the Earth. And then the second one will be a bit more specific on the lutetium, hafnium, and samarium neodymium decay schemes as well. So just to start with the first one, I thought I'd put up this chart, which is a chart of the nuclides and essentially maps out every isotope we know about, and with the y-axis here being the number of protons and the x-axis being the number of neutrons. And it's just a nice chart to get a sense of how radioactive decay works, really. All the stable isotopes, a lot of these black squares here, and then you can see that as you fall off that sort of very small island of stability, things get radioactive quite quickly. And, the more protons you get in your thing, or I should say, the more the number of protons and neutrons aren't balanced, the rate of radioactive decay increases quite quickly, and you get things that last for only a few milliseconds. So those sort of isotopes we're not going to have any use for, right? They don't live long enough. But the ones we will be more interested in, the ones that are longer lived, which sort of lie around the island of stable isotopes. So Chris and Pete have already given us a good introduction on how we can use radiogenic isotopes for geochronology. And as I said, this talk we focus more on the chemical fingerprinting, particularly using the long-lived isotope systems like your samarium neodymium, lutetium, hafnium, uranium, thorium, lead systems. And the first half of the talk will be more on the theory behind it, so how we fractionate parent-daughter elements. And then the second half of the talk and the following talk will be more on practical applications, so how we can use those to look at sort of the heterogeneity in the mantle and how continental crust grew. You can also use some of the shorter-lived systems for looking at stuff that happened really early on in the history of the solar system and early on in Earth's history, so sort of what timescales the core formed over. I won't really touch on those, but I'll put a little bit on sort of early Earth history from that perspective. And then some other more interesting applications are perhaps more towards geophysics, like sort of how can we evaluate thermal budget of the Earth using, what we can gather about the distribution of radioactive elements from isotopes. So just some definitions that Pete's already touched on. Isotope are forms of the same element that have different number of neutrons and therefore different atomic mass. Radioactivity is spontaneous decomposition of these unstable nuclei. And throughout the talk, I'll refer to these as parent isotopes or parent nuclei. And the process of radioactive decay generates radiogenic isotopes, which are often referred to as daughter isotopes. And then perhaps the most important definition to take note of here is this idea of a reservoir, right? So I've defined that as an isotopically and or geochemically distinct geological entity. These are things we tend to define using isotopes and refer to them as having some kind of character, either depleted or enriched, depending on sort of the nature of their isotopic composition. Stuck again. Okay, so very basically, what we start off with is some kind of radioactive decay scheme. So in this example, I have used the samarium neodymium decay scheme, which involves samarium 127, which decays to neodymium 143. And there's obviously a mass change of 4 during that process, so you have to kick out 1 helium atom or nuclei in the process. And there's probably some energy as well that comes off with that. The half-life for that reaction is quite long. It's 106 billion years. So we can use that decay scheme to write essentially an equation that describes how the isotopes that we're interested in will change over time, right? And that comes from our age equation. And what it shows is we can measure today the composition of 143 neodymium relative to some stable isotope 144. And that's going to be a function of how much 143 neodymium was in our sample when it was initially isolated, and how much samarium was also isolated in there at that same time, and then obviously how long we've had to ingrow neodymium. So in order to generate differences in isotopic compositions that we go out and measure, the first thing we need to do is to fractionate samarium and neodymium from one another, right? Because think of the Earth as a closed system. If you don't move samarium and neodymium around, it's all going to be the same, and over time it won't change. So, but luckily the Earth is quite heterogeneous, so we don't have that problem. And then the second step is we just have to wait, right? These things decay over very long periods of time, like sort of tens to hundreds of billions of years. So you have to wait quite a while in order to get measurable differences in isotope compositions. And from that kind of process, we can see that what we do when we measure isotope ratios is we're essentially measuring time-integrated element ratios, right? And particularly element ratios being your parent-daughter ratios. So things like rubidium, strontium, samarium, neodymium, uranium, lead, and so on. Just some notations that Pete's already touched on. Particularly for the very long-lived systems like samarium, neodymium, and lutetium, hafnium, you are looking at very, very, very small changes in isotope ratios. So we commonly measure them into 6 significant figures. And we convert them into these epsilon notations, which are essentially your parts per 10,000 relative to some standard, which in samarium, neodymium, and lutetium, hafnium is your chondritic uniform reservoir. You'll also see in some of the shorter lived systems this mu notation, which is parts per million relative to some terrestrial standard. I think those are the only two that I'll probably be using throughout the talk. Okay, so fundamentally what it comes down to then is trying to understand how we fractionate parent and daughter ratios, right? And in the context of so understanding how the Earth is differentiated, that comes down to essentially how we fractionate these elements during partial melting reactions. So you can think of, the simplest sort of way we can describe element fractionation during partial melting. So for instance, if you partial melt the mantle, you can generate some liquid, and then you also be left with the residual solid. And we can describe roughly how elements should separate between the liquid and the solid using our equations like this, which is just the simplest one we have for batch melting, which is derived by a simple mass balance. And what it shows is that the concentration of some elements, in this case I, over the concentration in our starting material, can be a function of 1F, which is the degree to which we melt that starting material, and then this value D, which is what we call a partition coefficient. It is essentially described as the ratio of element I in the solid and the liquid. And that basically says, like, if you take some material, you partially melt it, does that material want to go into the liquid or does it want to stay in the solid? Obviously, the previous equation I showed is batch melting, and that describes a situation where you keep the melt and the solid in equilibrium throughout the whole melting process, right? And obviously, when we talk about fractionation and differentiation, we don't want to do that. We want to melt something and extract it out and take it away and isolate those melts and residual solids. So to better describe that kind of process, we have a fractional melting equation, which is slightly different, but essentially has the same variables. And you can take two of these equations for two different elements, put them over one another, and you can come up with some equation that shows how an element ratio, so two elements I and J, should change as a function of degree of melting and the partition coefficients. And what you see is basically that for a given source composition, the element ratio that you get depends on one, the melt fraction, which is the same in both cases, obviously. And then it really comes down to the difference in the D values for those two elements, right? Not that I animated that, but that's basically what that's meant to highlight there. So, for given melt fraction and given composition, we're really just interested in the difference between the D values for, say, lutetium and hafnium. In reality, those D values are very complex, how you get them. So I won't go into the detail here, but they're a function of pressure, temperature, composition, and also they're element mineral specific. So they are, if you're interested in more, you can look at this paper by Blundy and Wood in 1994. They show that how these D values change 4 different elements. Basically depends on how well they fit into the crystal structure for specific minerals. And they came up with this complex model that actually fits experimental data quite well for most elements. So you can go down a rabbit hole on that, but for general principles, we can get some rough ideas about what these D values are that illustrate mostly what we see in nature. So just going back to our simple batch melting equation, we can throw in some typical values for D. So I've got on this graph here, D going from 0.001 all the way up to 10. And you can see that for D equals 1, there's no change, essentially. They lie along this 10 to the naught, which is just 1. But as soon as D is less than 1, the ratio of the concentration of an element in your liquid to your solid goes up. But if D is greater than 1, it goes down. And that's how we define whether an element is incompatible or compatible. So basically, incompatible elements tend to go into the liquid, so the concentration in your liquid relative to what you started with goes up, whereas compatible elements tend to go into the solid, so concentration in the liquid relative to what you started with goes down. And on the right-hand graph here, you can see I've thrown in approximate D values for parent and daughter elements that we're interested in, so things like uranium, thorium, lead, rubidium, strontium, samarium, neodymium. You can see they're all incompatible elements, right? But in some, and obviously uranium, thorium are most incompatible. Rubidium's pretty incompatible as well. And then things like lutetium and samarium are the least incompatible. These things are going to be composition specific as well. So the values I've calculated here roughly for mantle prototype with olivine, OPX, CPX, and spinel, which is something that might approximate what's in the upper mantle. But as soon as you go deeper than 60 kilometers, the dominant aluminium bearing phase is going to be garnet. So that changing phases will change the partition coefficients a bit, but generally, this is the sort of behavior you'll see. So yeah, what's interesting is that different parent-daughter systems behave differently, right? So for lutetium and hafnium and samarium, neodymium, the parents, being lutetium and samarium, are less incompatible than the daughters, right? But for rubidium and strontium, it's the other way around. The parent is more incompatible, so that's going to mean that the ratios of those two elements are different depending or in the liquid. So what you see here is basically the ratio of the concentration of two elements in the liquid versus what you started with, and that you see that the liquid is very much enriched in rubidium relative to strontium. So you can think of the case of partially melting the mantle and extracting crust. You're going to get a much higher rubidium-strontium ratio in the crust than you will in the mantle. But for things like samarium, neodymium, and lutetium, hafnium, it's the other way around, right? The daughter products are more incompatible than the parents, so the parent-daughter ratio goes down in the crust that you extract, and then will correspondingly go up in the solid that you're left with. And it's also interesting to see that these ratios are somewhat dependent or variably dependent on melt fraction as well. So for rubidium strontium system, mainly because of how incompatible rubidium is, it's very, very sensitive to melt fraction at very low melt fractions. Samarium, neodymium, and lutetium hafnium are less sensitive. But as you increase melt fraction, so say past 5 to 10%, that they're not so sensitive to the degree of melting. So
where does uranium lead come?
I have specifically left uranium lead off here because lead is a bit of a slippery element. Yeah, you'll see that if you look carefully at this graph here, lead actually plots higher. It's more incompatible than uranium, just from the way I've calculated the partition coefficients. But we know from measuring lead isotopes that it's not really. And that's probably because of other phases that might retain lead in the mantle that I haven't taken into account here. But this kind of just illustrates essentially the process by which we fractionate parent-daughter ratios. So you can see as we extract crust out of the mantle, we're going to fractionate parent-daughter ratios, and then in theory over time, the crust and mantle will evolve to different isotopic compositions. And this is just a spider diagram. So it's a diagram where we list the trace elements essentially in order of their compatibility. So the most incompatible elements down here, but things like rubidium, uranium, lead, and then the most compatible elements at the other end. And you can see the T-shin is one of the most compatible. And it's essentially a rock that's normalized to primitive mantle. Things that have a sort of negative slope in the incompatible elements here are depleted in incompatible elements. So that's typically what you see of oceanic basalts that form mid-ocean ridges, so morbs. Things that plot up here with this slope going down like that are enriched in incompatible elements, and that's typical of oceanic crust. So in this diagram, the gloss is a model for oceanic sediment, which is kind of average continental crust. Think of it like that. And what you see on average is essentially what I just illustrated using the partition coefficients, that depleted mantle that's had crust extracted out of it and is depleted is enriched in samarium relative to neodymium. And the converse of that is that the crust that you extracted is enriched in neodymium relative to samarium, relative to what you started with. And the opposite is true for the rubidium strontium system. So rubidium is much more enriched than strontium in the crust versus, and obviously depleted in the residual mantle. This is just what I've thrown in as a fun challenge from that sort of fractional melting equation. Oh, sorry, let me take the other way around. What you see is when you plot some specific element concentrations, or the log of those concentrations versus one another, is that you form these very nice linear arrays. So this is from a global mid-ocean ridge basalt data set. And it is possible to go from this equation, manipulate it mathematically to show why exactly those arrays form. And I thought I'd throw it out as a challenge to you if you feel like a bit of math. Yeah, you can actually prove that they should show these perfect linear arrays in log space. They're not always going to equal slopes of 1. If they do equal a slope of 1, it means those elements are behaving perfectly the same, and essentially their d values are identical. But as the slope changes, it tells you that d values aren't the same, and you're getting some fractionation between those elements. So here, yttrium and holmium have a slope of basically 1, so you can infer that the partition coefficient is identical, whereas potassium and thorium have a slope that's less than 1. So it tells you that uranium's probably slightly more incompatible than potassium. So why is that useful? Essentially, when you look at the composition of the oceanic crust, because it's very, very young on average compared to the age of the Earth, and also the sort of half-lives of all these radiogenic isotope systems, right? So the oldest oceanic crust you have in sort of the Western Pacific is maybe 160 to 180 million years old. I think there is some Permian crust in the Eastern Mediterranean, but it's very, very localized and small. What that means is because the age of these rocks is so small compared to the half-life, that this term in your age equation essentially goes to 0, right? So we don't have to actually worry about the radiogenic ingrowth in these rocks, and the composition we measure today is essentially equal to the composition in the mantle underneath that those rocks are extracted out of. And that's basically what this slide says, right? Is, we've melted the mantle to form the oceanic crust, and the isotope composition in that melt is equal to the isotopic composition in the mantle underneath. So by mapping out and looking at the isotopic heterogeneity in the oceanic crust, so your mid-ocean ridge basalts, your ocean island basalts, we can get a sense of what the compositional variation in the mantle is underneath. And people have spent the last 40 or 50 years doing just that. So they go out in these cruises and they throw a bucket attached to one piece of steel cable off the back, and they dredge rocks off the mid-ocean ridges. And you can also go to places like Hawaii and some of the volcanic islands in the Atlantic Ocean and look at the lavas that are coming out there and sort of measure the isotopic composition. And when you plot them all up together, you see there's actually a huge amount of heterogeneity. So this graph here, we're looking at 143 neodymium over 144 versus the 87 strontium over 86 strontium ratio. What you find is that mid-ocean ridge basalts tend to plot up in this part of the diagram here, whereas your ocean islands overlap that to some extent, but they also show a lot of scatter sort of down to quite high or radiogenic strontium compositions and very unradiogenic neodymium compositions, which are more characteristic of continental crust. But there's other components in there as well. So what that is showing you is that your mid-ocean ridge basalts, like we saw in the spider diagram, are coming from something that's been depleted in incompatible elements. So enriched in strontium, relatively speaking, so it evolves to higher 143 neodymium values. But your ocean island basalts are picking up some material that has seen the opposite of sort of fractionation history, right? So it's been depleted in samarium or enriched in neodymium, you might say, but also enriched in rubidium, such that it can grow to very radiogenic strontium isotope values. And that essentially, suggesting that deep down in the source of some of these ocean island basalts is material that was initially extracted out of the mantle and then buried back in there, right? So it's showing you that there's recycled continental crust deep down in the mantle source of some of these ocean island basalts. When you look at other isotope systems, so in this graph on the right here, we're plotting 87 strontium versus 86 strontium versus 206, 204 lead. So looking at the uranium lead decay scheme. And you see that kind of almost sort of binary mixing array here is broken up into multiple different mixing arrays, right? So you've got your DM component here that's mixing with this EM component here, which people call enriched mantle. And in many papers, you see that's actually broken up into two components. So I think this is EM1, but you'll find that this end member here is called EM2. And then there's this high mu component, which its characteristic feature is that it has very, very high 206, 204 or lead isotope compositions, which implies a source that was very enriched in uranium. It's still quite debated exactly what these reservoirs represent. I think most people would agree that this EM2 is sort of average continental crust because it kind of plots where you'd expect average continental crust to plot. But EM1 is clearly quite different isotopically. I don't think we know exactly what that represents. And high mu as well, it's it clearly doesn't have the strontium isotope composition that you'd expect upper continental crust to have, but it's very enriched in lead, which you kind of need to explain. So yeah, another interesting feature of this diagram is that they're all kind of, these fingers all track back to something that's somewhere down there, and that's what people call this prima or FOMO component. And they think that that's kind of maybe what the best estimate of probably primitive mantle might be. And it's also a bit curious that there's clearly mixing between prima and all these components individually, but there's no mixing between the other individual components. So yeah, I don't know exactly what that means, but it probably says something about how this stuff is stored down in the mantle. So another way we can get at this is by looking at the noble gases as well. So Pete and Chris have already mentioned that, especially for these alpha decay reactions where you're changing the mass quite a lot, that the reason you change the mass is because you kick off all these helium nuclei, and particularly for uranium and thorium, there's a huge change in atomic mass, and that's because you kick off quite a lot of helium nuclei. And we can measure the helium isotope ratios in these rocks as well, and that also tells us something about what's going on down there. So again, I put this diagram back on as a reference. And then these two diagrams here show, again, the neodymium isotope ratios versus the lead isotope ratios, but color-coded according to the helium isotope ratios. So the dark blue squares are things with very high 3 to 4 helium ratios. So 3 helium being primordial helium that's formed during sort of nuclear thermostatic processes during early solar system history, whereas helium-4 is helium that's produced through alpha decay, mainly from uranium and thorium. High helium-3, helium-4, obviously that indicates a very primitive kind of unradiogenic or mantle that hasn't seen a lot of crustal input or input from a source with high thorium and uranium content, whereas the low helium-4 ratios reflect the opposite. And you see that the pattern we identified using the neodymium and samarium isotope system will reflect in the helium isotopes as well. So the depleted mantle has high neodymium and very primitive helium isotope compositions, whereas your enriched reservoirs and particularly the high mu has very, very radiogenic helium isotope compositions. So suggesting that those sources we see again have been contaminated by material that probably been recycled from the continental crust. We can also apply this sort of thing to continental environments in circumstances where we look at rocks that formed over a very, very specific or short, narrow time interval. And that means essentially when you look over a narrow time interval, there's very little variability that reflects long-term isotopic evolution from radioactive decay, but essentially, all the rocks formed in that time will sample the isotopic heterogeneity in the crust. And I've been doing a lot of lead isotope work on the Yilgarn craton the last couple of years. So Pete mentioned you can measure lead isotopes in galena. You can also measure them, not to quite the same precision, but reasonably well in orthoclase or K feldspar and granites. And when you plot the sort of 2:7 versus the 2:4 ratio, you see there's quite a lot of isotopic variability in both galenas and the granites from the Yilgarn craton. You see some very low 2:6, 2:4, and low 2:7, 2:4 ratios that probably reflect something like mantle compositions, but there's also scattered to high 2:7, 2:4, and high 2:6, 2:4, which might be more indicative of an older crustal component. With the uranium lead system, we kind of have three systems for one. So we can also plot the 208, 2:4 versus the 2:6, 2:4. And when we do that for the material in the Yilgarn, you see that older crustal component actually gets broken up into two distinct reservoirs, right? So there's a high 208, 2:4 reservoir that has 208 compositions that are much higher than what you'd expect the mantle at that time to be. And that implies that you must have fractionated thorium and uranium from one another sometime previously. So we've got some models here which show that fractionation had to have happened between 3.8 and 3.3 GA. You also have a lower 208 crustal component here, which has mantle-like thorium, or the 208-284 composition implies a mantle-like thorium-uranium ratio, which essentially means it's unfractionated. And you can also map that out spatially because we've done quite a lot of samples and show that these high 208, 204 granites lie in these regions where from zircon data, we know are found on bits of very old crust. What's interesting here is that we also know that there's something missing, right? So we touched on when we're looking at the partition coefficients, this idea of complementarity, right? When you partly melt the mantle, you fractionate things into a liquid and a solid, right? So if we think that to fractionate the thorium-uranium ratio, generate these high 208, 204 compositions, you need to partially melt some crustal source with a mineral that tends to retain thorium, but not retain uranium, essentially, right? And we have monazite, we know does that in metamorphic environments. But what it implies is that you've lost uranium, right? And you've extracted a melt that would be then preferentially enriched in uranium, but not in thorium, which would be the complementary reservoir to that component, if you can think of it. And we don't see that anywhere in the Yilgarn. So that's quite interesting from that perspective, is that, I mean, maybe that composition down there, you might argue, would have, evolved from here at a lower thorium-uranium ratio than the mantle, but for some reason, that material seems to have been removed and we don't sample it. And that's kind of what that diagram illustrates there. That you've just got green stones in the Yukon might represent your massive components. And then you've got the crust, which you can divide into sort of more mantle-derived granites and the older high thorium uranium components. Another example identifying these kind of fractionation processes is using another isotope system of samarium neodymium, which is your 146, 142, which is a very short-lived system. So the half-life is about 70 million years. So it's pretty useless for looking at things that happen like on modern Earth, but it's used in early Earth. So back in the early 2000s, people identified these rocks in Greenland with sort of very high 142 mu neodymium values, which implies that they were formed from a source that had been depleted in samarium sometime prior, right? So very early on in Earth history. And they hypothesized back then that there has to be, you've clearly fractionated samarium neodymium early on in Earth history. There has to be some complementary enriched reservoir that must go with that. And then Annika Rizzo and I think it was in the paper in 2012, I put it on there, found some dikes again. I think these are from Greenland as well that have correspondingly low initial 142 neodymium values in the sample and enriched reservoir. So again, it's going back to this idea that what we use radiogenic isotopes for is looking at past chemical fractionation processes. And from this data, you can infer that there must have been some fractionation of samarium and neodymium that happened probably very shortly after Earth accreted. So I think to get these compositions they model, it had to have happened within, maybe 100 million years of the accretion of the Earth, and could reflect some kind of primordial crust, crystallization of an early magma ocean that has, we don't see it in any magmas younger than 3GA. So presumably that material has been completely recycled back into the mantle and homogenized. So we don't see any of that variability. I mean, you do see it in these younger rocks, but I don't know exactly where that's from. But definitely in the modern mantle, it's all homogeneous, and we see no evidence of it at all. So this, I thought I'd put on at the end as a nice example of how to use radiogenic isotopes, not for necessarily identifying anything that's useful for geochemists, but probably something that's more useful for geophysicists. So we know that plate tectonics is essentially an expression of heat loss from the Earth, and that heat has been calculated to be, or the heat flux from the Earth is 46 terawatts essentially, and that's comprised of two components. There's obviously the primordial heat that was left over from accretion of the Earth, but then there's also the heat that's generated through radioactive decay subsequently. How that heat is distributed is quite important for driving different processes in the Earth. So if all the heat's in the crust, it's not going to be very useful for driving things like mantle convection. But particularly for looking at things that happen in the core, if you have a significant amount of heat in the core, then you can start to drive the geodynamo with radiogenic heat. And geophysicists are quite interested in how much of the heat that runs the geodynamo, which ultimately runs Earth's magnetic field, is just from primordial heat versus radiogenic heat. And there's a very interesting paper by Scott Whipperfirth and co. who use a mass balance, essentially saying, we know how much uranium is in the crust and the mantle roughly, and we know roughly what the Earth should be based on what we see in primitive meteorites. So we can get a sense of how much uranium is in the core just based on that mass balance. And you can't, and there's a complicated way of manipulating those equations to recast in terms of things we can measure using lead isotopes, so your kappa values, which are your thorium-uranium ratios. And they derive this equation which shows that the thorium-uranium ratio in the core is a function of this decay value, which is essentially a partition coefficient between uranium, between the core and the silicate Earth. And then thorium-uranium ratios in the continental crust, and the thorium-uranium ratios in the mantle, which we can measure. Oh, got stuck again. And basically plugging in those numbers that they measure, they end up with a graph like this, which shows to get Earth to equal the value we see in primitive meteorites in terms of its thorium-uranium ratio, you don't need very much uranium in the core. So 0.16 nanograms per gram, which is parts per billion, so it's essentially zero, which tells you that there's very little radiogenic heating happening in the core. It's all mostly primordial heat, and that all the radioactivity is confined essentially to the crust and the mantle. So I think just a bit over time, but closing off that thing, essentially what I've tried to demonstrate is that what you measure with radiogenic isotopes are just time integrated measures of past chemical fractionation events, essentially trace element ratios. And that we can infer something about when they happening, or sorry, getting a muddle. We can infer that those fractionation events happened, say something about the magnitude of those fractionation events, and in some cases also say something about the timing. There are obviously lots of radiogenic decay schemes out there, but they are kind of application specific. So the very short-lived systems, we've obviously burned through all the nuclear fuel for those systems. They're not going to be very, very useful for looking at chemical fractionation that's happening today, but they can tell us something about events that happened very early on in the history of the solar system and the early Earth history. And in terms of crustal differentiation and the more longer-term evolution of Earth, we're going to be looking at these longer-term decay schemes.